Welcome back. Time for physics. This is video lecture 24.2, and the first section we're going to discuss is section 2 in chapter 24, in which we're going to talk about what are called equipotential surfaces and their relationship to the electric field, which is also what we've been talking about in lab most recently. So here's the key idea, kind of like a question. How can you find the potential difference between 2 points, delta V, if you already know the electric field that's in that region of space, E? How do you find delta V between 2 points in space where there's an electric field E and you know the electric field? That turns out to be a rather important question, because there are commonly times when we do know what the electric field is that's been created by some distribution of charge, and then we want to know the potential difference between various points. So the answer to this question is based on two ideas, both of which we introduced earlier in chapter 24. First, the electric force is a conservative force, and so there's an electric potential energy that goes with it, and the relationship is right here. The work done by the electric force is equal to the negative of the change of the electric potential energy. That's idea 1. Idea 2 is this. The potential difference, delta V, between 2 points is equal to the potential energy change, delta U electric, when a charge moves between those 2 points, divided by the charge. We're going to call the charge here Q0. We're going to assume it's positive, and we're going to call it a test charge. Now I want to show you how those two ideas together lead to the equation further down on this screen that's in that red box, which is the important equation. So let me start over here to the side and take this idea that the potential difference between 2 points is equal to the change in electric potential energy per unit charge when a charge moves between those points, and that the change in the electric potential energy is the negative of the work done by the electric force on the charge Q0. And then we remember the formula for how to calculate the work done by a force in general. I'll bring the negative 1 over Q0 out front, and the general way you calculate the work done by a force is you take the dot product of the force, in this case the electric force, with a tiny little infinitesimal displacement ds along a path from the initial point to the final point. You can take any path you want between the initial and final points, because that path integral for a conservative force is path independent. Any path will give the same answer. Okay? Then what we remember, I'll just write it down here, is that the way we think about the electric force on our particle Q0 as it moves from the initial point to the final point is that it is that particle's charge Q0 times the electric field that's already there. So Q0 times E dot ds. But then I see that defining potential difference as potential energy change per unit charge gives me a benefit here, because I have a factor of the charge Q0 upstairs from the electric force and a factor of the charge Q0 downstairs from the definition of potential difference. Those cancel. So the calculation of the potential difference between 2 points is just the negative of the line integral from the initial point to the final point of E dot ds, the electric field that's already there. And that's what's there in the boxed equation. Now the picture is also trying to show you what we're talking about. You've got a set of field lines. Those are the blue, and in this case curved, somewhat curvy lines with arrows pointing in the direction of the electric field at any given point. And then somebody has chosen an initial point in space, I, and a final point over here, F. And we're going to take a little positive charge called a test charge with charge Q naught, and we're going to move it along a path, this one, from I to F, okay? And that we show the particle there at a certain point. And we also show the next little displacement, ds, that it's about to complete, right there, the blue arrow I just drew, tangent to the path at that moment. And then it also shows the electric force on our particle there. That's the purple arrow I just drew, Q naught times E. E is the electric field that these field lines are depicting. And you can see there's an angle, theta, between the E and the ds. And so when we do that dot product, E dot ds, like we've written over here, we have to take the magnitude of the field E times the magnitude of that tiny displacement ds times the cosine of that angle theta. And that will be whatever it is for that little step right there. Now we're going to do that same process for all the little steps between point I and point F. Okay, and there are an infinite number of them. And we got to add up the results we get to get the grand total. Okay? And that's called a line integral. And that's what you do to get the potential difference between 2 points if you already know the electric field that is there. You pick a path between the 2 points in question, I and F, and then you do this integral, negative E dot ds. And my advice is, when faced with doing this actual integral, pick a path for doing the integral that follows the electric field as closely as possible. You get to pick any path you want from the point I to the point F. Now, there are some examples in Chapter 24, Section 2. There should be, I believe, a sample problem for doing a line integral, and I'm going to do one for you in a completely separate video lecture, a bonus one that will be coming also over the weekend. But here's one thing to note. Because of that minus sign in that formula connecting delta V and this line integral of the electric field, it basically means this. If the path that you're taking from I to F is more or less downstream in the direction of the electric field, it flows, if you like, with the electric field. If point F is more downstream than point I, then the potential difference in going from I to F, the delta V, will be negative, meaning the potential at point F is less than the potential at point I. And so here's a very general point that's very useful to remember. The electric field points in the direction of decreasing, emphasize, decreasing electric potential. And that's all because of that negative sign that you see in that boxed equation. Now let's do a little bit more simple geometry than this picture here shows. Let's take this down just a little bit. And let me squeeze this down just a little so it's a little bit smaller. Okay. Let's talk a little bit about what's called an equipotential surface, by which we mean a surface on which the electric potential has the same value at every point. And remember, the unit of electric potential is the unit called the volt. And in fact, in the previous experiment, you mapped out equipotential lines, we called them, because you were limited in your dimensionality there. On the two-dimensional surface of that black conducting paper, you could only draw equipotential lines. In all of three-dimensional space, you have equipotential surfaces. And so an equipotential surface is a surface in space in which the electric potential has the same value in volts at every point. And here's something we're going to show with that little line integral formula I just introduced, and which you used in lab. Equipotential surfaces are always perpendicular to electric field lines. Okay? And I want to talk about that in the context of a specific situation. In the case where we have a uniform electric field, E. Uniform means that at every point in a region of space, it has the same magnitude and the same direction. And this uniform electric field is represented by a series of equally spaced electric field lines, all pointing from left to right, and equally spaced, like that. That would be produced, for example, that's one way to think of it, by somewhere over here to the left, an infinite planar sheet that goes up and down vertically and in and out of the screen towards you and away from you. Infinite in extent, planar sheet with uniform surface per unit, charge per unit surface, charge per unit area, surface charge density, sigma. Then that would produce a uniform electric field pointing to the right. Okay? All right, now I want to show that electric field lines are always perpendicular to equipotential surfaces. And we use this line integral expression that we just introduced relating delta V and E. Delta V equals negative integral of E dot ds. Let's write that down right here. Negative integral from point I to point F of E dot ds. And the picture down below is still in the same region, okay? And it shows a point I over here to the left and a point F to the right of it there along an x-axis that points to the right, okay? And the electric field line pointing from left to right. So the electric field vector at any point in space points to the right and has the same magnitude and direction because it's a uniform electric field. All right, now, first I want to show that electric field lines must be perpendicular to equipotential surfaces. What if we imagine in this integral that points I and F are on the same equipotential surface? So not what I just talked about down there, but maybe like right about here for I, and maybe right about here for F. Then, and I'm going to take a little step ds on that equipotential surface from I to F, okay? So ds is along the equipotential surface. Well, then we know what the delta V must be when we step from I to F, like along here, taking little ds's that way, because those are both on an equipotential surface. Then we know that delta V has to be 0, because point I and point F are on the same equipotential surface. And that's what an equipotential surface means, that every point has the same potential V, so the delta V must be 0. So the line integral from E to F of E dot ds must equal 0. Now, how is that going to happen? It's not because the ds part is 0, and it's not because the E part is 0. Neither of those is 0. So how do we get this integral to be 0? It's because of the dot product between those two. Okay? If it must mean that the direction of the displacement you took, ds, and the electric field must be exactly at 90 degrees to each other, because then their dot product vanishes. Okay? So E must be perpendicular, that vector must be perpendicular to your little ds, and your step was along the equipotential surface. So E is perpendicular to the equipotential surfaces. Well, the electric field lines point to the right. So the equipotential surfaces must be up and down. And I'll draw some of them here. I'll draw them in red. Now you're looking at a flat plane on the side, so it looks like a line. And I'm drawing a series of them, a family of these equipotential surfaces. And they're equally spaced, and the delta V between each of them is the same. Okay? And that is a set of equipotential surfaces in red and electric field lines in blue that go with the uniform electric field of an infinite planar sheet. Now let me come down here to the situation. Let me get myself some space here. That is below there. Okay? Now I want to look down here. Same situation. Uniform electric field pointing to the right. We've picked a point I and a point F, and we're going to do a line integral. There's the path we're going to take. And notice it's right along the direction of E. If possible, pick a path that mimics the direction of E. It'll make doing the line integral easier. So we're going to apply delta V equals negative integral from I to F of E dot ds. Well, what you do is you imagine breaking up that path into a whole bunch of little ds's. I'll just draw one of them right there. Those would be tangent to the path. And you got to imagine a whole bunch of them, one after the other. Okay? And then I'll draw the electric field vector right there. E arrow. Well, it just points to the right, just like the ds does. So when we do this dot product up here, we'll have delta V equals negative integral from I to F. Magnitude E times magnitude ds times the cosine of the angle between E and ds. They both point in the same direction, so that angle is 0 degrees. Cosine of 0 degrees is plus 1. So we have minus the integral from I to F of magnitude E, magnitude ds. Now, because the field is uniform, remember, you can bring the E out front. So let's do that. Delta V equals negative magnitude E, and then I'm left with an integral of a bunch of little ds magnitudes from the initial point to the final point. But that'll just be the total displacement from point I to point F. And the picture shows that here, below. They call it delta x. So the resultant here is negative magnitude E times delta x. And if you have a uniform field, that's an easy way to calculate the potential difference between 2 points. Take the negative of the magnitude of the field times the displacement. Now it's got to be the displacement component, in this case it happens to be delta x, along the direction of the field. That make sense? Okay. Only that displacement component along the direction of the field. Okay. That's why we picked the path the way we did. Go straight along the field. It makes the integral easy. All right, let's look at another one that's not quite so easy, but we'll just draw pictures for now. Just a simple, single particle with positive charge. That's it. Well, then we know what the electric field lines are like. They point radially outward, away from the positive charge. And they do go on for onward, dot, 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 right? We just stopped drawing them. And they go on around like that. You can see more of them there, okay? Those are the electric field lines. And you have to remember that they really do radiate outward in three-dimensional space. But in any vertical plane that you do a cross-section, they look like this. Now, the equipotential surfaces, in this case, have to be spheres. because the surface of a sphere will be intersected perpendicularly by a radial line. Remember, the equipotential surfaces and the electric field lines must cross each other at a right angle. So here's one of the equipotential surfaces. There's an infinite number of them. There's one for each possible value in volts. Okay, so that's an equipotential surface. It's the surface, in this case, of a sphere. And where the electric field line crosses it, that surface, it crosses it at a right angle every time. Okay? Now, the spacing of the equipotential surfaces are constant amounts. Like between these two, between those two equipotential lines, there and there, it might be 1 volt. But then these two here, which are closer together, is also 1 volt. And then between the two outer ones, okay, the third one and the fourth one, it's also 1 volt. And the fact that they're getting farther apart is a way of showing you that the field is getting weaker. Okay? All right, so here's you got a case where the structure is a little more complicated. You have radiating outward electric field lines, where the magnitude of the electric field is getting weaker as you go farther from the charge. And your equipotential surfaces are spheres, spherical surfaces. Okay? And if we told you what the charge of the particle was, Q, then we could pick any 2 points, like there, I, there, F, tell you where those points are, and you ought to be able to calculate the delta V between those 2 points using the negative integral of E dot ds. Now, if that's not clear to you how that would happen, we would do that, this is where you want to watch the bonus video I'm going to send a little later. I'm going to do in that bonus video the following example problem. I'll state it now so that your brain can start thinking about it. And you can even try to think for yourself a little bit about how you would do it and maybe even try it for yourself. But then watch the video lecture I'm going to send where I work it out. And so in this example, we are to find the potential difference between 2 points given the electrostatic field that has been created by some charge distribution. In fact, here's the charge distribution. It's a sphere of radius big R that has positive charge big Q uniformly distributed throughout its volume. It must be a non-conducting sphere. We've got 2 points, A and B. See them there? It's pretty clear where they are. They're marked with X's. There's point A, there's point B. The radial distance of point A from the center is half big R. And the radial distance of point B from the center is 3 times big R. We are to compute the electrostatic potential difference, delta V, equal to VB minus VA between those 2 points. Okay? All right, that's what I will do in a separate video lecture. But I urge you to think about it a little bit and maybe even try it for yourself before watching that video. Okay, now, in the meantime, let me go on to talk a little bit about Chapter 24, Section 3, where we're going to look at the expression for the electric potential due to a single charged particle. Okay? All right. Here's the key idea. Any charged particle Q creates electric potential V of R at every point in space. It's a field. It's a potential field, which is a scalar. Electric potential is a scalar. Now, this same charge creates electric field at every point in space, a vector field. Now we have a scalar field, electric potential as well. And when we write V of R, we're saying the electric potential at a point that is a distance R from the charge. So here's our big question. What is this function V of R for a single charged particle? We're going to use this integral relationship. Delta V is the negative line integral from point I to point F of E dot ds. And we're going to integrate from an arbitrary initial point P to infinity. Oh, we're going to take the final point to be at infinity. I'll explain why in just a minute. So let me temporarily expand the view so that you can see what we've got. See the little positive test charge? Or I shouldn't call it test charge. The positively charged particle, Q? It's fixed in place, can't move. It creates electric field everywhere. They're trying to represent that by drawing these electric field lines that point radially outward. And of course, they don't just terminate, they continue radially outward in every direction from the positively charged particle. There's a few of those electric field lines. That's showing you the E, right, from that charged particle. Then they've taken this green line, just going straight through and going on up in the screen, plane of the screen, and they're going to pick a point P right there on this line. Point P, is a distance big R from the charge. And we're going to start at that point P, and we're going to integrate along a radial path going upward in the plane of the screen all the way to infinity. And then we're going to all choose together. We're all going to agree that for a single charged particle like this, we will assign the value of the electric potential at an infinite distance from the charge, the value of 0. If you're infinitely far away from this charged particle, we will by definition say the electric potential due to that particle is 0 because you're infinitely far away. And now let me show you how we use the line integral approach to find the formula. What I want to find, just so it's clear for everybody, is the electric potential V at that point P. Okay? All right, here we go. Delta V equals the negative of the line integral from the initial point to the final point, E dot ds. In the picture here over to the side, let me zoom out again so you can see it, has chosen an arbitrary point there on the path and shows the little displacement that's going to happen, ds, and the electric field there, E. You see why they're drawn that way? The ds is along the line because that's the direction we're traveling, and the electric field is along that line because that's away from the charge. Electric field points away from positive charge. Okay, so the E and the ds are in the same direction. So when we do the dot product, we'll have magnitude E, magnitude ds, cosine of the angle between the E and the ds, which is 0 degrees, and the cosine of 0 degrees is +1. Now let me put in expressions for these other things, like the magnitude of E. Well, remember I said this procedure only works if you already know the electric field. And I mean the formula, the symbolic expression. And so for E here, that would just be, in this case, Q over 4 pi epsilon 0 little r squared, where little r is the distance from the charge out to this point where we are. That's a little r, okay? Because that's the formula for the field of a point particle. We learned that in chapter 22. Now for the ds, what you want to do is you want to write that as a tiny radial step, dr. Okay? All right, so with all those terms in there, let's see what the delta V formula looks like now. Actually, let me go ahead and expand out the delta V. That means V final minus V initial. And so that's going to equal negative integral from I to F of Q over 4 pi epsilon 0 little r squared times d little r. But remember where point F is, the final point? Way out on that line, way out at infinity. where we decided by definition that the electric potential had the value 0. So that means the electric potential at the final point is 0 because the final point's at infinity. And so the final point corresponds to a radial distance of infinity. And the initial point corresponds to a radial distance from the charge of big R. Remember, we started at point P. Notice there's a negative sign then left on, there's a negative sign left, on this side of the equality, and a negative sign on that side. So I can multiply both sides by negative, and those are gone. Okay? And now I'm going to change that V initial to just V at point P, which is distance big R. So then I can also bring out front all the parts of the integrand that are constant. That's the q and the 4 and the pi and the epsilon 0. And then I have the integral from big R to infinity, d little r over little r squared. And now we talk about doing that integral. First, let's write it like this. Q over 4 pi epsilon 0, integral from big R to infinity, little r to the minus 2 d little r, right? Bring it upstairs. Now, don't be thrown off by if that integral looks weird to you. Just think of the pattern of the very first integral you learned. X to the n dx is x to the n plus 1 over n plus 1. Where in our case, x means r, and n means negative 2. So let's see what we've got then. Q over 4 pi epsilon 0, negative 1 over little r. In other words, little r to the minus 1 over minus 1, with the limits from big R to infinity. And I think I just have room here to fit this in. V at point P, which is a distance big R from the charge, is, well, let's bring that negative out front, negative q over 4 pi epsilon 0 times 1 over infinity minus 1 over big R. To a physicist, 1 over infinity is 0. 1 over huge is small. You can't get huger than infinity, and you can't get smaller than 0. And then I've got two negatives together. Those cancel, so I end up with q over 4 pi epsilon 0 big R. And that's the electric potential right there at the point P, which is a distance big R from the charge, with the reference point being at infinity. Then what all the books do is they say, well, don't call the distance that little p is big R. Little p could be anywhere. Just replace the big R with a little r that stands for an arbitrary distance. And you have this very famous result for the electric potential of a charged particle. Now what that means is you calculate the potential V at a distance little r. Okay? From a charge q. And it's q over 4 pi epsilon 0 r. Careful, not r squared, just r. We'll use that a lot in this chapter. There are some tips for this, using this new result I want to mention briefly. First of all, this is a scalar expression. There's no arrows on anything. Nothing is a vector. No components. No direction. Just a scalar potential. The result for V depends on two things. The amount of charge that you had, or the particle has, q, and the distance r from the charge. It is derived assuming that the potential equals 0 as r goes to infinity. And the sign of V depends on the sign of q. Now, we did all this calculation assuming that the particle up here that was causing everything was a positive charge. And then we got this formula for the potential. It's a function of distance. But it can also be used for a negative charge. All right, the q could have been a negative quantity. Then the electric field lines would have pointed radially inward. But the formula still works exactly as is. But then when you plug in the number for the q there, it's going to be negative. That's all we're saying. Okay, just a little bit of practice just to show you that it's really quite easy to work with electric potential. Easier than working with electric field. How about the electric potential of a particle? Okay, I don't know why it says that. Just ignore that. Let's look at this application of electric potential for a point particle. We're going to use this result to find the net electric potential due to a system of two or more charged particles. See the red dots? Those are all charged particles. Like there's particle 1, there's particle 2, there's particle 3, dot, dot, dot. Each one has charge Q, same Q. We have picked a point C. There's no charge there, but it is at the center of the circle that these charges are sitting on. And the distance there from the center to the circle is big R. Here's the question. What's the net electric potential at point C? What is the net electric potential due to all of those charges at that center point, C? We'll just use that formula up above for the potential of a charged particle and use it for each one, and then add them all up, and it's scalar addition. So for example, V1 at point C, the electric potential from charge number 1 at point C. Well, that's just Q over 4 pi epsilon 0. How far is the charge from point C? Big R. Right? That's the distance from the first charge to point C. What am I going to get for V2? What's the electric potential at point C from charge 2? Did you say it's the same as for charge 1? Q over 4 pi epsilon 0 big R. Because charge 2, with the same amount of charge, Q, is the same distance from the center. Well, now maybe you're starting to get the point. Since we're on a circle there, all the charges are going to produce the same potential at the point C. And there are 12 of those charges there. Count them. So the V net is simply 12 times the V from any one of them. 12 times Q over 4 pi epsilon 0 R, which that happens to be 3Q over pi epsilon 0 R. And that's what you get. And that's how you would find the net electric potential at the point C in that case. Note that it isn't that simple finding the net electric field at point C from those 12 charges. There you got to worry about directions. You might want to think a little bit about what that would be. The net electric field at point C from those 12 charges. I will just leave you with one more thing, a class engagement question for Blackboard. Okay, here's what it says. This figure shows 3 arrangements, each arrangement consisting of 2 protons. Protons, remember, have positive charge by an amount little e. And in each picture, the protons are represented by the red dots. So in picture A, there they are. And then there's a point P. I like to mark it more with like a little X. No charge at point P, it's just a point on an axis like that. Okay? And what we're interested in this little exercise is the net electric potential V produced at point P by the set of 2 protons. But what we've got is we've got 3 geometries. In geometry A, the 2 protons are along the same line. You can see the various distances there. In geometry B, the point P is here, and 1 proton is over here, and 1 proton is down there. What's the net electric potential at point P? And in picture C, the point P is right here, and 1 proton is to the left by a certain amount, and 1 proton is to the right. And again, your job is to find an expression for the net electric potential at each of the 3 places, and then rank them from biggest to smallest at the point P in each case, okay? And we'll be talking in class about the electric potential of a point charge. But that's all for this video.